Hi everyone, welcome to part 12 of organ technology. In this series we take a look primarily at analog organs and how they work, but sometimes we dabble a little in the digital world and take a look at pipe organ stuff from time to time. Today we're going to have our third look at my old Rodgers 33E. This was a theater organ model that Rodgers engineered in 1967. It came out in 1968. My particular copy was from about 1971, and we've been taking a look at how that instrument works and some of the interesting repairs that needed to be done. So last time I showed you the power supply and its suspicious capacitors, and we also have taken a look at the fact that there was an excessive amount of audio hum on this instrument. Obviously that power supply needed to be repaired, but I wasn't entirely certain that that was the source of the hum. I was going to do my normal thing of working backwards through the audio path, but one of the viewers, one of you out there, suggested, just start with that main power supply since that's problematic, and we did so. So, the first thing I want to say about these videos is that I am not presenting these as how-to videos. What I'm telling you is presented as information for entertainment purposes. I am not suggesting that anybody try to tackle any of these repair jobs themselves unless you are already an expert in working with electronics equipment. And there's good reason for that. Working with electricity can be dangerous, so please be careful out there. So during my college days, I was primarily a music major, but I've always had an intense interest in electronics. And so I did take some electronics courses, and I actually have a certification in what's called industrial electronics. One of the classes was a class primarily about transistors, and we were tasked with building circuits. And what they would give us to work with was a schematic that was a little bit like the recipes if you've ever watched the Great British Baking Show, where they give the bakers these really sketchy recipes that don't really have all the instructions and the big box of ingredients, and then they're expected to make a certain thing, like a certain cake or bread or something. Well, the schematics we would get in these classes were very much like that. We'd get like an amplifier or switching circuit, and it would have the layout of the components, but it wouldn't necessarily have the component values. And one of the particularly maddening things they did was that they would draw a symbol for capacitors that didn't show the polarity of those capacitors and how they were supposed to go in. Well, capacitors, if they're put in a series circuit in the wrong direction, they will generally explode. Now, fortunately, we were dealing with fairly small components, but basically every last one of us exploded a capacitor at some point. There was one kid in particular who managed to explode a capacitor on pretty much a daily basis, and naturally the rest of the guys in the class were not nice about it. I'm sorry to say we could have helped him more, but teasing him seemed like more fun at the time, I guess. Any rate, so we learned a lot in that class, and I learned a lot about being safe, handling things correctly, and capacitors in particular are something that have to be dealt with very carefully. Fortunately for me, to redo this power supply, I have the schematic, and so I can look at the schematic, carefully figure out where those points are on the actual circuit board to make sure I get those capacitors of the correct size into the right location. So the original capacitors are these canister types, and the interesting thing about the way these are built, this outside rim here is the negative side, and then there's a tap point in the middle, more or less the middle, somewhere in the middle of the capacitor, that is your positive terminal. And these types of capacitors are interesting, these canister types, because you can have multiple taps. You can see on this one, we've got our outer rim, but then we've got also 2 points at which it's tapped into. These are exactly the same size, and in the configuration on the power supply, the one with a single tap was a 2000 microfarad capacitor, and the one with the double tap was a dual 1000 microfarad capacitor. And then we're replacing them with these little electrolytic capacitors, which are actually rated at this one's slightly higher. It's 2200 microfarads. This one's 1000 microfarads. These were rated at 35 volts. These are rated at 50 volts. So obviously this style of capacitor is a lot more efficient. Now the trick is, of course, we got to get those old capacitors out, get these new capacitors in, and we have to get them in carefully in the right way so we don't cause other problems. So while I was doing this job, I took some pictures. And so first, when we set up, we got to get the power supply on the bench, and then the basic tools I used for this are solder wick and my soldering iron. Now, solder wick is pretty good at removing solder. You put the solder wick on the surface where you're trying to soak up the solder, and it does a decent job of that. The better tool is they make these desoldering tools that it's basically a heat gun with a vacuum pump on it, and you put it on there, it melts the solder, and you press the button, and it sucks that solder right out of there. Those are really very nice. Here we're looking at the back side of the circuit board, and we have several points that we have to remove the solder so that the old capacitors will come loose, and that's where the solder wick comes into play. This is a close-up of some used solder wick. It basically, the braided copper just soaks up the solder. You know, this stuff is not cheap, and it takes quite a bit of it to soak up bigger solder joints. Here's a nice comparison. Once I got all the old canister capacitors out, I'm showing the replacement capacitors, and that gives you a really good size comparison. One of the things I always do when I'm putting components into a circuit board, technicians with more experience than me are more confident in their quick and accurate soldering skills, so they don't put these heat sinks in, but I do because I sometimes linger with the soldering iron a bit. The heat sink basically it just does that. It soaks up excess heat so we don't damage the component when we're using a hot soldering iron. And here is the power supply with the replacement capacitors installed. And again, this is with careful examination of the actual schematic, making sure that I know what goes where. The 3 capacitors on the top side of the photo, closest to the big, really large canister capacitors, those are all installed with the positive side of the capacitor going to ground. And the 3 ones on the lower, you have another 2200 microfarad capacitor in there, and then the pair of 1000 microfarad capacitors. Those are all set up with the negative side to the grounding terminal of the power supply. And that's, of course, so that those capacitors are going to do their job accurately. That's kind of why we exploded a lot of capacitors in that class I was telling you about, because it's not always completely obvious when you're looking at a complicated circuit. If you're looking at a straight-up series circuit, which direction to put the capacitor in is fairly obvious if you understand what's going on. In a parallel circuit, it's not as obvious, but generally, if it's a straight up parallel circuit, if you put the capacitor in backwards, it just isn't going to do anything. But sometimes, depending on the arrangement of the circuit, you can explode these things, and so that's why I tell you, don't mess with this stuff unless you know what you're doing. I'm just telling you this for your own entertainment and information. So let's take a moment and go out to the shop and see the organ all set up, and you'll notice there's no more hum. Okay, so here we are. It's up and running, and notice that hum is gone. And all we did was fix the main power supply, but I also, the audio modifications using the different amplifier, it's just a more compact setup, and I don't know if that had any impact on it at all. Now, the one thing we do have that's going to have to be fixed next, on the big crown amplifier, the first channel doesn't work. And I opened it up, and it's not very tinkerer friendly in there. So rather than try to fix that, it's going to be easier to fix the amplifier that was in the Leslie speaker, and so that's on the bench now. Again, needs a capacitor replacement, so that's what we're going to do, and then we'll put that back in the Leslie, and that'll take the place of that channel. For now, I just have the tibia sound mixed into the main audio here, and it works just fine for now. So we'll get that fixed next. I have hooked up some basic effects devices. I have chorus on the main channel. I have pitch shift on the brass channel, and that improves the ensemble of the instrument a little bit. It also has digital reverb. So let's see if we can... Sounds like a theater organ. Now, the next things that are going to have to be maybe dealt with on this, the percussion circuits are not behaving right, and I don't know that I want to go to the trouble of fixing those. While Rodgers had the best percussion circuits at the time, they're still synthesized percussion circuits and don't sound all that great. Plus, they're kind of interlaced with the pipe voices, and so, like for example, if I turn on the harp, since that's taken from the tibia, it shuts down the tibia tremolo, so I can't really use them together. The piano does a similar thing off of the main generator. I have a little multi-timbral synthesizer box that has decent percussion instruments on it, and ultimately I want to add that somehow, but then I have to somehow get a MIDI output on this thing. So figuring that out will be another interesting video, right? Trying to add MIDI to a 1967 designed electronic organ might be a fun thing to do. But at any rate, it's up and running. I can make some music on it, and that's the best way to find out what's next. So after the last video we did in the Organ Technology series, a viewer wrote in and asked a very good question. Why did Rodgers use reed relays instead of solid state circuits for their stop switching in the organ? So to kind of refresh your memory, when we hit the keys, we have a keying circuit that sends an audio signal from the oscillators over to a series of reed relays. These are controlled by the stop key switches, and what happens is we've got our signal from the oscillators kind of always coming in, and then we need to route it to various filter circuits, and that's done with these reed switches with the electromagnets to trigger them. Well, obviously there's plenty of transistors in these organs. Why didn't they use a solid state, transistor switch of some kind in place of these reed relays, which is an electromechanical system? Seems kind of primitive even for 1967. And when the viewer wrote the question in, I really didn't have a great answer because I hadn't spent much time thinking about it. And I got to thinking about it because they had sparked my curiosity, and I think I've come up with an interesting answer. So let's take a look at the physical stop switches. Now, obviously, no organ builder really builds absolutely everything that goes into their organ. And Rodgers has usually used stop key switches from Reisner. They sometimes use, there's other manufacturers like Klon and so forth. These switches, of course, were built for pipe organs. And the way these are constructed, we have this metal frame here, and one side of each of these magnets are for the combination action, so that when I hit a piston, if the stop needs to be on, this magnet fires and moves the stop into the on position. If a different piston needs this stop to be off, it fires this magnet and boom, we turn it off. Or we hit the key with our stop key with our fingers and down it goes. Well, let's look at how this is done electrically. We have one side of the magnet to the frame. Then we have the other side out here isolated for potentially our positive. But then we also have this tab. And there's a contact point which is mounted here and makes contact with that tab, this tab right here, when the stop key is down. Which means that whatever our voltage is on the frame here, our common voltage, that's going to go out to our stop control. Now in the case of a pipe organ situation, it's going to be triggering some kind of magnet. And the fact that you've got that voltage mingling there doesn't matter. We've got magnets here. We're going to be using this to switch other magnets. No problem. But inside the 33E, it's an audio signal that we have to switch. So we need some kind of isolation between this switch and its voltage and the audio signal which is being switched. Now, could we have used a transistor? Well, yes and no. Remember that inside a transistor, ultimately your collector signal and your base signal are going to mingle. They're going to merge and head out to the emitter. So if we're running a switch, just a simple switch where I have to, say, turn on and off a 12-volt signal with a 5-volt signal, that's no problem with the emitter and collector combining, the collector and the base combining and heading out to the emitter. But if we have a 15-volt switching signal and an audio signal, well, whether I put them on the collector or the base, they're still going to combine at the emitter. And that's obviously going to, cause a noise issue. So the reed relay was an easy way to have circuit isolation between the switching circuit and the audio signal. Now, could you do a transistor switch that will do this and still have the isolation? Yes, you can, but it becomes extremely complicated. So back in 1967, using the reed relays was probably the better of the two solutions. This is simple, it's reliable, it gets the job done, and it is compatible with this old style switch. Of course, as we fast forward into the future, as pipe organ circuitry, switching circuitry became more sophisticated, it was necessary to do more sophisticated switching. Now here we have a more modern stop switch. Again, we still have our two magnets for operating our combination system, but now we have a magnetic reed switch. And so when this switch is on, the reed switch closes. More importantly, it is completely isolated electrically from our two magnets and the frame. So this switch would be able to either trigger a transistor switch in place here, or for that matter, well, you could route the audio signal right through that reed switch. More likely, this enables a simplified switching over here that would be solid state and work as needed. So there's nobody at Rodgers today that I can talk to who was around in 1967 when the 33E was engineered to verify this. But it seems pretty obvious to me when we look at the difference between a modern stop key and one available in 1967, that because of the way voltage is intermingled on this system, the best and simplest way to create a circuit isolation so that we didn't introduce DC voltage into our signal path, into our audio signal path, we would just use the reed relay. The other thing we talked about in part 11 of this series was some of the speakers I'm using for the 33E. One of them being a custom variation on a Rodgers speaker system. And another viewer asked if I would do a video about Rodgers speakers that were used with the various eras of analog organs. Speaker systems were a big part of the system because they were ultimately part of the filtration that made those oscillators sound like an organ. And so the speakers used in the early analog organs and the speakers used in the later analog organs were very different, and there were engineering things that went along the way to really make those speakers work just right with those instruments. So yes, I will do a video on speaker systems for analog organs, and that's going to require a little bit of research and gathering of pictures and drawings and schematics and all of that good stuff, so it might take a little while. So if I get all that done before the next video, I'll do it then, but it may be a couple videos down the road to really do it properly. So what's next for the 33E? Well, we've got a number of modifications that might be coming up. First of all, I have to fix the Leslie speaker. Got to fix that amplifier and put it back in because one channel of the crown amplifier doesn't work. I have inserted some effects devices, as you saw earlier, to kind of liven up the sound of the instrument. And there's going to be more stuff like that. So thanks for joining me today, and we'll see you next time.